Hello, welcome to another concept session. So today we're gonna take on the issue of Newton's laws of motion in any frame. In particular, we're gonna talk about what happens when a frame is accelerating. So from the last episode, you probably remember. If you haven't done this, then you can go back to the last episode. We talked about a very special type of frame called inertial frame. In that frame, Newton's law of motion says that for one body, just one object of mass m, we can think of this as a particle of mass m. You can think this is a particle of mass m. So on one side you're going to have force on that particle, but everything else, and the other side is going to be mass times acceleration of that particle. So this is Newton's second law of motion. And then Newton's third law of motion is about two bodies, which you can say this is a particle of mass m1, this is a particle of mass m2. So you look at two particles or any two objects, okay, and force on 1 by 2 is a negative of the force on 2 by 1, meaning their magnitudes equal but then opposite direction. And these forces don't have to be, so like if I have 1 here and 2 here, then force on 1 can be that way, it doesn't have to be along the line acting. Then force on 2 have to be exactly same length, so this guy will have to be exactly opposite in direction but same magnitude. This is the third law of motion. Okay, we want to be able to write law to be have a form, mathematical form of this law in any frame, not just inertial frame. This one is true in all frames, so I want to be able to write in all frames. Right? So we only know how to that the form takes this simple form only in a special frame called inertial frame. So we want to write this in a non-inertial frame. Non-inertial frame. So where do we find that? What is the characteristic of non-inertial frame? So from the last time we also said that here is this universe, and we can say this is the center of the universe, and this is, we can just say it's at rest. We're just going to claim it, and everything else will be with respect to that. And this is just a really ad hoc assumption. We don't know, we can't verify it because we don't know where the center of the universe is and it's actually whether it's maybe moving, but this is something that you can approximate at 2 different degrees, and we learned how to approximate, and I'm not going to repeat all the arguments. So any frame that's moving at a constant velocity, so this frame itself is 0 at rest, so with respect to itself 0, but here is a frame that may be moving with respect to v not equal 0 but constant. Okay, so if you look at a particle, look at a particle p here, and you say, okay, law with respect to that, this frame 1 and this is the frame 2, and law with respect to that, both is going to take the same form. Why? Because acceleration of p with respect to frame 1, this is frame 1, is equal to acceleration of p with respect to frame 2. So as long as velocity is constant with respect to this at rest frame, they're all going to have same. And so on this side is force is independent of frame. If this side is same, then you're going to get force on M in frame F1 is equal to M A in frame F1, but this is same as frame F2, and so this is also the same on M in frame F2. So these are all inertial frames. The only criteria needed is that this frame, like this frame, has a constant velocity with respect to this absolute rest frame. And so to the degree that that's true, you can just use this willy-nilly, you know, just like we can use this on Earth's surface if we're not thinking the surface of Earth and the time that's involved and the acceleration of the surface of the Earth is not that great and not going to make a big difference. So this is a picture of inertial frame. Now, how do we do a non-inertial? So here is a frame. Say let's call it F3, but some point O. Let's call it O prime. Let's call this guy O. So with respect to this frame, this guy has an acceleration. Maybe this is accelerating in that direction. So there is maybe a star using, okay, fix the star, and then, but that star is accelerating with respect to the central universe like that. Then you will find that so this is the acceleration of the frame. So you will find that F on M in frame F3 is not equals to mass and acceleration in frame F3. It's not equal to that. And we will now find out what should be the relationship. There's a little correction you have to do, and we're going to work out that correction. Okay, so we're going to work out in step by step. We'll start with this very simple frame, which is it just has a given acceleration, just like that. Okay, all right. Okay, so drew a simple picture. So this is the inertial frame, and this is a non-inertial frame. At instant t, that's the situation, and this particle is moving along, and there's at this instant force is F on this, F on M. So at this instant, that's the force. So we want to write law for this. So first notice that in as far as inertial frame is concerned, we already know F on M at this instant equals to mass and A of M in this frame, so in inertial frame, and this is a non-inertial frame. Okay, so this is inertial frame. So now what is that? Well, we can actually write that out. If this is R at instant t, that's the from origin to the place where the particle is. So this is just equals to M dr dt square. That's by definition. Okay, so this is my equation. This is from the second law, standard form, right? Now we want to figure out how to write this in terms of that, in terms of non-inertial frame. So we need this vector which locates where the O prime is, and let's call this vector maybe script R, and let's call this other vector so this is the vector that locates non-inertial guy will locate, and there's going to be R prime vector. So you look at this triangle of vectors, this I'm calling R, this is calling script R, and this I'm calling R prime. So this plus this equals to that. So R plus R prime equals R, and we already know if I take a 2 time derivatives, I'm going to get this guy dr. So this is the acceleration of the frame with respect to inertial frame. So this is the AF, acceleration of n non-inertial frame with respect to the inertial frame, and then this is going to be R prime dt square, and that's going to be the acceleration of this particle with respect to the inertial frame. So let's call it IA prime, and this is acceleration of a particle with respect to non-inertial frame, and then I do time derivatives of that. There's nothing but the acceleration, this thing. So just call it A, acceleration of particle, it's the same particle but with respect to inertial frame. And this one, let's just make it same notation. So we know we can use this, right? So we can just plug this in there. So we're going to get equation for this. So plug this in there. So we plug this in there. So we're going to get on the left side is going to be force on object M, which is same in every frame. Mass times frame plus with respect to this frame of the same particle. Now you can see I want to write F equals ma in this, but won't be. So this is what will be the law in non-inertial frame, second non-inertial frame. Well, you could say I can transfer this on the other side, and so all I'll be left with is mass times A prime. So this is equal to F on M minus M of the frame itself, excess frame itself. So this quantity here acts like another force, but this is the actual force. So what we should call it minus this thing is called fictitious force. Fictitious force or fake force. So writing over here we say F on M plus fictitious force equals mass times A prime. So this will be the law, and fictitious force will be minus m of the frame itself with respect to the inertial frame. So whenever we do, actually inertial frame is always in the background. It's always there. It never goes away, because this thing is referring to this is with respect to an inertial frame. So this is acceleration of non-inertial frame with respect to the inertial frame. The inertial frame is always going to be there. So whenever we do a problem, we always have this. So acceleration frame can be just accelerating body, or it can be a frame which is rotating, like frame that's fixed to the surface of the earth is rotating, so that would be necessary to take into account when we do physics in a frame which is rotating with earth. That kind of frame will be a non-inertial frame. Okay, so we're going to do some examples. The rotating frames, I will do it in another episode, because this has some really interesting, especially math and other properties that go with it. Okay, let's do a problem, an example problem, just to illustrate this idea. This will be a very simple example. So what's given is a block attached with a spring constant K, and this block mass m is also given. So if you look at the inertial frame, so if you look at just inertial frame, it's much easier to state it. This spring is attached to the back of the truck, and the block is not really sliding, it's just staying still. Of course, the whole thing, this entire thing, is accelerating with A. So every particle of everything that's with the truck is accelerating with A with respect to this inertial frame. In the non-inertial frame, the situation is very different. So the frame itself, so maybe it should not like that. Frame itself has an acceleration. Frame itself has the acceleration in that direction with A. And the block is not accelerating here. So in this frame, block has zero acceleration. In this frame, the block has acceleration in the x direction of magnitude A. So acceleration is A I hat. So this is the inertial frame, so the law will be this. So if you look at the block, it's accelerating in that direction. So, and magnitude A, that means the spring must be pushing it. These two have to be the same. This force must be that to actually match up. The right side is this way, the left side has to match up, and this has to be some K times delta L. Well, if the force this way, the spring is going to apply a force that way if it's compressed. So spring has, this is the equilibrium. So this has to be, delta L has to be compressed. Delta means compression. For the force to be that way, pushing this. That's the way spring force works, right? Okay, so from here we can say K times delta L equals mass times A. So delta L equals MA over K. So we really didn't need the non-inertial frame. We just did everything in inertial frame. This is the standard way of doing this problem. Let's do it a little bit non-standard way. In this one, what do we have? We have acceleration of the block, so we're going to do this way. So acceleration of the block is 0, so the right side is 0. So that means in this we have a force that's going to has to come from a spring plus the fictitious force has to be equal to 0. The fictitious force is that, right? So this one is everything along the x-axis, x direction. So fictitious force x component is, if this is that way, then the force in the opposite direction is going to minus ma x component, and so that should be minus m. Now a itself is a I hat, so this is the ax ma. So we got the fictitious force. This one, that we can write. Let's look at what the fictitious force is. So we have the block. Fictitious force x component is negative, meaning this is the direction of the fictitious force. And fictitious force plus the force from the spring cancels out. It just tells me the spring must be this way. Therefore, F has to be that way, which, according to this, again, same kind of logic as this, makes it compression. That means spring is compressed. Okay, so we have a K, so F x component is K times delta L. It's in the positive direction, and delta L, I'm going to use a positive magnitude. So K times delta L, so these two together gives me K times delta L minus M times A equal to 0. Then delta L equals to M A over K. Same answer, but done it in a different way. Just where you put things. It's very simple. You can see clearly what different components you need. Okay, so we can do another example. Okay, this is another example of where it's easy to see. So here is someone riding an elevator. So this is an elevator, and elevator may be going up or down, doesn't matter. The acceleration of the elevator is upward in this problem. Okay, you can always set it up for downward, but this is I'm going to do for upward. And this person is sitting on a scale, and you can read how much he weighs at that point. Okay, so the question is, when the elevator is going up, what the scale will read? Will it read mg? So you know, when the acceleration is 0, the scale reads mg, right? And the question is, why does it read mg? So if you understand that, then you'll be able to actually set it up and answer this question. To understand this, you actually have to look at what does the scale read. The scale reads the normal force. Okay, so here's the scale, and when the person pushes down on this with a normal force, then the scale is pushing up on it with the same normal force, and that's the force that the scale reads. So it reads this or this, but one of this is forces in the scale from the top surface, and there is a other force in the scale is m is scale g, and there is a normal force from the floor. So this is where the scale, but the scale is reading these forces. All right, so now if you look at the person over here, it has mg. So this is person, forces on person, forces on person, mg, and it's this normal force. So if we can figure out the normal force is, that's what the scale will read in every situation. So this will be the diagram, and over here from the setup, the elevator's acceleration gives me the acceleration of the mass of the object, of the person also. So this, as a result of this thing, this whole thing has an acceleration a and the mass m, acceleration a. So over here the acceleration is equal to a, this acceleration. So set it up, y component, so this is going to be Fn minus mg equals to, this is also positive, ma, a is equal to capital A. So the Fn is mg plus a. So that's what the scale will read. So that's the answer, doing all inertial frame. So the question is, what do you do for the non-inertial frame? Same thing. Okay, so it works out a little differently. Over here the frame has the acceleration that way. So the fictitious force, again I'm going to do y component. So the y component of force will be along positive y, negative ma, because it is minus a times the acceleration of the frame. Acceleration of the frame is pointed upward, so this is the MAF, and there's a negative in front of it. Okay, so that's the fictitious force. How about the A prime? When I'm this frame, there is no acceleration, so here the A prime is equal to 0. So again, F, let's look at what are the forces on these guys. You have an mg and you have an n, Fn. So you have Fn minus mg, these are the forces. Then you have a fictitious force which is minus ma equal to 0. And then solve this for Fn. Once again you can get mg plus a. Pretty cool. So you can see from these examples, the effort is more or less the same, but it's just way how you think about it. More complicated problems, I will do it in another video. Another video would be a rotating frame. How to write the acceleration of the frame when it's rotating with respect to the inertial frame. And that's actually a very cute and interesting problem in itself. How do you write the acceleration of the frame? Like, how do you get the acceleration of the frame if the frame is rotating instead of just translating? That will take us into a little bit more difficult mathematical problem, but we will do it in another video. Okay, so I'm going to stop here. See you in another episode. Bye.